He was a child, curious like every other child, with boundless imagination and endless questions. A child with the potential to change the world, just like every child. But this child was destined to change the world. His name was Albert Einstein. This is the Einstein we all know, a wise old man with an extraordinary mind, as if he just appeared out of nowhere. Yet, he too was once a child, shaped by a past, molded by a story that made him who he was. This child's story began on March 14, 1879, when he was born in the small German town of Ulm. At a time when German Jews were just beginning to own land, receive higher education, and pursue various professions, Albert was born as the first child of a Jewish family, Pauline and Hermann Einstein. Later, his sister Maya would join the family, and Albert enjoyed a happy childhood. His mother, Pauline, was a strong, bold, and intelligent woman. In many ways, Albert took after his mother. His father, Hermann, a mattress salesman, encouraged him with new business opportunities. Hermann was also a man fascinated by science and the latest technologies of his time. Albert's curiosity was first sparked by a gift from his father, a simple compass. Albert was 4 or 5 years old when he held the compass, and no matter which way he turned it, the needle always pointed in one direction. He was mesmerized by this ancient yet simple technology. Later, he would recall, "Until then, I believed you had to touch something to move it." But at that moment, he realized there was a much deeper force behind how the world worked. This deeper force was electromagnetism. Thanks to the contributions of scientists like Faraday and Maxwell, electromagnetism became one of the most significant discoveries of the 19th century. This fundamental force of nature would lead to a technological revolution within a few years. Germany was quickly transitioning from kerosene to electricity. Hermann Einstein, a skilled entrepreneur, saw an opportunity and moved his family to Munich, where he established a factory producing electric dynamos. Thus, Albert grew up surrounded by electricity, machines, and the mystery of electric power. He was also very fortunate. His uncles and family friends would often tell him about electricity and the principles behind how machines worked. At a young age, he was already exposed to the subject that would become the foundation of his work. Electromagnetism was the family business, and electromagnetism would also be Albert's business. By the time he was 10, Albert was already developing himself, studying a geometry book he found, which he would later describe as life-changing and call his sacred book. He would devour every popular science book he could find. Contrary to popular belief, he never got tired of studying or reading. But there was one thing he despised: school. The rigid, creativity-stifling system of German society and culture at the time reflected an authoritarianism that suffocated him. When he reached high school, he faced another obstacle. The time to join the German army was approaching. In 1894, Hermann Einstein made a radical decision to move his factory to Pavia, Italy, in response to growing competition, and decided to bring his family along, all except Albert. Albert stayed in Munich to finish school, but as mentioned, he disliked school. He constantly clashed with his teachers and school administration. One day, having reached his limit, he went to a doctor, was diagnosed with extreme exhaustion and burnout, and received an indefinite leave from school. He left, never to return, and took refuge in Italy with his family. At 15, Albert had made the radical decision to leave school. He reassured his family by saying, "Don't worry, I'm no fool. I have a plan." His plan was to somehow finish high school and qualify for the entrance exam to the Swiss Polytechnic University. He had some time to prepare, and meanwhile, a chance to relax in his family home in Pavia. According to his sister Maya's friends, Albert's greatest joy was to ride his bicycle around, lost in his thoughts. Freed from the pressures of school, he also spent time in his father's factory, experimenting with electricity, trying to understand this force more deeply. For many, these years would later be seen as the most important time that shaped Albert into the Albert Einstein we know. The laboratory at the factory had become an incredible playground for him. So, the brilliant theoretical physicist Albert Einstein had actually gained a lot of practical experience as well. But there was a problem. Albert still didn't have a high school diploma or even citizenship. Yes, he had given up his German citizenship to avoid military service, and after failing the arts section of the entrance exam for the Swiss Polytechnic, he had few options left. His father arranged for him to attend a high school in the Swiss city of Aarau. Reluctantly, Albert started attending this school, which would prove to be a significant turning point in his life. This school was nothing like the system in Germany. It had a fantastic physics lab and a more traditional yet open approach to education. Here, he found the freedom, excitement, and intellectual space he had been looking for. It was in this environment that he first tasted what it meant to be a scientist. In the lab, he would connect compass needles to batteries and observe how electric currents created magnetic fields. He would discover that these forces were actually different forms of the same underlying force, something he needed to see with his own eyes because he wouldn't believe without seeing. He took a magnet and watched how iron filings formed patterns. He also learned that light was actually an electromagnetic wave traveling through space. And that was when he found his life's purpose. Yes, at just a teenager, Albert's famous thought experiments began to take shape. He imagined what it would be like to ride on a beam of light, as if riding a bicycle. His thought experiments simplified even the most complex ideas by turning them into playful explorations. He asked a simple question: if light is a wave, then no matter how fast you go, could you catch its peaks or valleys? If one could ride along with this wave, what would we see? Would light remain constant? Would time stand still? Or could you travel endlessly on the peak of that wave, experiencing it as a moment frozen in time? Of course, these were difficult questions for a young boy who had just finished high school at 16, but he had set his mind to it. After graduating, he enrolled at the Swiss Federal Institute of Technology, one of Europe's top institutes. At this school, equipped with one of the best laboratories in the world, he would receive the finest education if only he could regularly attend his classes. It seemed he had an aversion to school, so he spent hours at the famous Odeon Cafe in Zurich, a place still operating today. He would sit there with friends, discussing ideas for hours. Two of these friends would become his closest companions, Marcel Grossman and Michel Bessot. And then there was a woman who caught Albert's attention. A woman who had traveled alone from Hungary to attend the Swiss Federal Institute of Technology, one of the few universities in Europe that admitted women. Her name was Mileva Marek. She was incredibly confident, intelligent, and free-spirited, which greatly intrigued Albert. Her independence, her ability to stand on her own, fascinated him. Their correspondence began around this time, with Albert expressing his admiration and becoming more romantic than ever. Meanwhile, Marcel Grossman, who excelled at mathematics, helped Albert prepare for exams by lending him his notes. Though Albert had to occasionally attend classes, he often got into trouble with his professors and the administration. A disciplinary record from March 1899 shows that he received a punishment for insubordination. Even in his electrotechnology lab course, he scored as low as a 6. In subjects he liked, he performed well, but for others, he paid no attention at all. His attitude, often perceived as arrogance, led him into verbal conflicts with the head of the physics department, Professor Heinrich Weber. Professor Weber would tell him, "Albert, you're incredibly smart, but you have a big problem: you don't listen to anyone." But Albert wouldn't back down, replying, "Why should I listen to him?" Professor Weber believed that physics had already been thoroughly explored 70 years prior, and that there was nothing left to discover. Albert would say, "When I present my own ideas, he doesn't even listen. Why should I listen to him?" The ideas he spoke about always circled back to light questions and experiments about light. His thought experiment about riding a light wave showed him that very strange things could happen at the speed of light. All the great minds before him believed that if light was indeed a wave, it had to travel within some kind of medium, like waves on a lake. But what was this medium? For a long time, scientists thought it was a mysterious substance called ether. According to 19th century physics, ether filled every corner of space and controlled the movement of light. Normally, measuring speed is simple. You calculate a car's speed or a boat's speed based on a fixed reference. A car moving at 100 would indeed be moving at 100 for someone standing still, or at 80 for someone in a car moving at 20. But was light like this? Did the speed of light depend on the ether? When scientists tried to measure the speed of light with ether as a reference, all their efforts failed. No matter what they tried, the speed of light remained constant in all directions. While the physics world wasn't ready to accept this, Albert had already dismissed the ether in his mind. This mysterious substance couldn't exist. Light was an exception, independent of all the laws governing motion. In 1900, however, Albert had just graduated and wasn't in a position to prove this yet. On top of that, his dream of working at the university was shattered due to his conflicts with Professor Weber. Meanwhile, his father's business wasn't doing well either, and Albert urgently needed a job. He sent letters to every institute and university he could think of, with no professor left uncontacted. Even his father stepped in, writing to a few universities on Albert's behalf. But Albert was left stranded. No institute or university would hire him. Albert Einstein was rejected by universities. To make matters worse, his personal life wasn't going well either. His family, especially his mother, disapproved of his relationship with Mileva. His mother thought Mileva was too independent and said, "She'll never be able to cook for you, so your socks or take care of a child." She even threatened, "If you marry her, I won't give you my blessing." Meanwhile, Mileva wasn't doing well academically and failed her exams. When his mother mockingly asked, "What will happen now with your beloved Mileva?" Albert replied, "She will be my wife, of course." Around this time, Albert invited Mileva for a romantic holiday by Lake Como. But the outcome of this trip would be unfortunate, especially for Mileva. She became pregnant, unable to complete her studies, and returned to her family in Hungary to give birth. In 1902, a daughter named Lisa was born, a child about whom very little is known, and who was tragically unlucky in many ways. In his letters, Albert seemed to suggest he wanted to give up the child. During this time, with the help of his friend Marcel, Albert finally found a job at a patent office. He didn't want to risk losing this job due to any scandal, as it had been hard to get. Meanwhile, Lisa fell ill, and soon after, all traces of her disappeared from history. According to some sources, Lisa passed away, and Albert never met his daughter. Around this time, Albert's father also fell gravely ill. After giving Albert permission to marry, he passed away on the same day. Following these dramatic events, Albert seemed changed, but perhaps not as deeply as one might expect. Emotions were perhaps his weak spot. He often insisted that he shouldn't let emotions affect him. He would say that he was unaffected by the deaths of his father and daughter. This detached approach, however, didn't bode well for Mileva. Though they were happy for a time after marrying in 1903, Albert soon became engrossed in his work, especially in his physics problems. Mileva, the brilliant woman who once captivated him, now took a back seat, caring for their home and their second child, Hans Albert, born in 1904. For Albert, however, things were going well. He had a job, a family, and could now immerse himself in the physics problems he was so curious about. Strangely, he also enjoyed his boring job at the patent office, as it gave him the peace he needed to solve his problems without pressure. Alongside friends, including Michel Besso, he formed a club they called the Olympia Academy. They would go on nature walks and engage in discussions about physics, science, and philosophy. Then came 1905 as Annus Mirabilis, the miracle year. By this time, Albert was sure of one thing: the speed of light remained constant, no matter the circumstances. This was a revelation. Speed, after all, was a measure of the distance traveled over time. If the speed of light was constant, then something else had to give. Light had begun to shine in his mind, illuminating the world. He asked a simple question: what if time isn't constant? It was a basic question, challenging assumptions held for thousands of years, assumptions that people didn't dare to question. Albert posed this question to Michel Besso during one of their nature walks, asking for his friend's help, not that he needed it. He spoke non-stop, even leaving Besso behind mid-sentence and rushing home. The next morning, Albert thanked Besso, saying, "I found the answer to the problem." Once, Albert expressed his thoughts, "It's as if only I asked these questions, as if only I tried to find the answers. People see them as childish questions, but maybe it's because I never stopped being a child. I've always had a childlike, insatiable curiosity, always trying to ask the simplest but most important questions. I still wonder, could God have created the universe differently? If I were God, how would I have done it?" Albert was trying to understand the mind of God, and sometimes he thought he could, catching glimpses through a tiny window, seeing a single line. His was a mind boundless as a child's, and in the end, his story is not one of the answers he found, but of the questions he dared to ask. His story would continue, just as it always had. You're amazing, my dear friend Michel. Amazing, I've finally found the answer. Michel Besso, before he could even ask the answer to what, was interrupted as Albert continued, "Are we in agreement that two events occurring at the same time are simultaneous?" Michel answered, "Of course, no." Albert replied, "This is a big mistake. Now imagine this with me. We're standing beside a ghostly railway track. There are two electrical poles, and we know the distance between them. Let's mark the exact midpoint between them. You stand there holding a mirror. Now, imagine lightning strikes both poles at the same time. If you look in your mirror, you'd see both events happening simultaneously. Now, board a train that passes through this area, holding a mirror that shows both sides. When the train reaches our marked point, lightning strikes the poles again. This time, do both bolts strike simultaneously?" As Michel thought, Albert answered himself, "No, of course not. In the mirror, you'd see the lightning strike the pole ahead of the train first. The light from the pole would take time to reach the mirror, and the train would have moved forward slightly, so the light from the pole behind would take even longer to catch up. It would look as though one struck before the other. To someone on the train, the bolts would appear to strike at different times. To someone standing beside the tracks, they would appear simultaneous." Michel interjected, but this, to which Albert replied, "Yes, my dear friend Michel, time is relative. As they say, sometimes a spark ignites a fire. Sometimes that spark changes only you, you're no longer the person you once were. Other times that fire spreads to every mind, changing everyone, changing the world forever." Was this Albert's spark? This railway thought experiment was that flash of enlightenment that changed everything. These kinds of thought experiments, especially this insight, seem so simple now, don't they? Albert himself once said, "There's nothing extraordinary, illogical, or mysterious here. I'm just trying to express that time flows at different rates for all of us." He often wondered why others struggled to grasp this simplicity. Just 5 weeks after arriving at this insight, he had written down all the evidence in a paper, which we know today as the Theory of Special Relativity. In its simplest form, the theory tells us that the faster you go, the slower time will pass for you, compared to someone standing still. In his paper, Albert suggested a way to visualize this effect. Take two clocks, place one at the equator and one at the pole. The clock at the equator would tick slower than the one at the pole. He said this in 1905. As simple as it may sound, this concept was hard to comprehend. On your way to work, time passes slower than when you're sitting at your desk. For a car moving at 100 kilometers per hour, this difference in time is so minuscule it's imperceptible. But if your car or bus could somehow reach 90% of the speed of light, strange things would happen. For instance, to someone standing by the roadside, you would appear 40% shorter. In fact, this insight answered the question Albert had pondered at age 15. What would happen if you could ride on a light wave? The answer was, nothing would happen. Yes, nothing at all, because at that speed, your length would shrink to zero and time would stop for you. If anything did happen, you wouldn't even be able to observe it. Of course, people at the time thought this idea was crazy. What you're saying is unprovable nonsense, they'd tell him. But every time it was tested, it worked. Special relativity had been discovered this way. In June 1905, when Albert was just 26, he submitted his paper on the electrodynamics of moving bodies to the German physics journal Annalen der Physik. The paper contained no references to previous work, no mention of anyone else, except a single note of thanks to his close friend Michel Bessot for patiently listening. He didn't mention his wife, Mileva, though some researchers believe there was an intellectual exchange between them on the subject. If Mileva had contributed, why not mention her? Some sources suggest that Mileva's involvement was similar to Bessot's, a listener, capable of understanding and commenting, but ultimately just a listener. As noted in earlier letters, Albert didn't have much time for intellectual debates with Mileva, though perhaps he should have acknowledged her contribution. However, Albert's personality was somewhat emotionless when it came to relationships practical, viewing emotions as unnecessary and highly ambitious. In fact, his theories had become everything to him, perhaps even more than his family. We can say that in 1905, his annus mirabilis, or miracle year, Albert seemed to lose control. He began publishing groundbreaking ideas on the quantum nature of light, the particle-like behavior of light, and the existence of atoms. To paint a clearer picture, this was a time when even the existence of atoms was still in doubt, and science faced significant opposition. As ideas built upon ideas, special relativity led to the formulation of one of history's most important equations. Equals 2E equals mc.2, meaning that the energy of an object is equal to its mass times the speed of light squared. We're talking about an astonishing number, Albert said. Even in just 1 gram of matter, there's an unbelievable amount of energy, but you wouldn't observe it unless that energy was released. It's like a wealthy man who dresses plainly and never spends any money. No one would know he's rich. No one would know how much energy he has. At 26, this patent office clerk was beginning to make a name for himself. His ideas were gradually spreading. Since he received no payment for his theories, he continued his office job and even took on tutoring. Meanwhile, professors from nearby universities, curious to meet this young physicist, began visiting the patent office, asking to speak with Albert. After graduation, he had applied for assistant positions, but he hadn't even received a response. Albert wasn't fully aware of where his theories would lead. His sole focus remained challenging himself and his ideas. Rather than resting after the success of his groundbreaking papers published during his miracle year, he noticed a shortcoming in his theory. In 1907, while revisiting special relativity for another physics journal, he suddenly stopped writing. He had realized something. His theory could explain almost everything in contemporary physics, except one thing: gravity. Under normal circumstances, very few people would dare to touch it. Gravity was well established and worked perfectly, aside from a few small issues that could change everything. Imagine a scale. Place 1 kilogram of iron on one side and 1 kilogram of cotton on the other, and it balances. That's because Earth's gravitational pull affects both equally. But here was the problem: how did Earth manage to do this? How did the iron or the cotton feel Earth's gravitational pull? Newton had said that this force governs the solar system. The planets followed a law, a rule of motion. Yet even Newton couldn't explain how gravity affects the entire universe, or how this force controls everything. This was the mystery. How did all the planets follow a specific path? What created this kind of order in the universe? Albert had once said, "I want to understand God's way of thinking." Max Planck, however, warned him, You're playing the biggest gamble of your life, Albert. Don't touch gravity. You can't solve it. And even if you did, no one would believe you. It's too complex, too difficult. For centuries, no one has dared to attempt this. Stay away. Albert knew it would be challenging. He once said, "Special relativity was child's play compared to this. I feel like my head is going to explode. I've never struggled this much." The greatest problem was that gravity was the most democratic force in the universe. It affected everything equally, whether it was you, me, a fly, a neutron star, or a galaxy. No matter its size or material, everything was equal in the eyes of gravity. Albert had no starting point, no exception he could use to approach this problem. No matter what he tried, he didn't know how to tackle it until he said, "Der glückliche Gedanke means Lebens," the happiest thought of my life. In that moment, the answer appeared on its own. It was a thought experiment, a new window through which he could glimpse God's way of thinking. A modern physics historian and editor of the collected papers of Albert Einstein, Martin Klein, once said in an interview, "If I could travel back and ask Albert Einstein one question, I'd ask, how could you be so sure of the principles you based your theories on? How did you know the law of relativity was this universal? How were you certain it would work in every part of the universe's fabric?" Indeed, the theory he developed seemingly in an instant was, in fact, the product of decades of thought. Since he was gifted a compass by his father at age 5, he had continuously pondered these problems. His moments of enlightenment were actually the result of years of intellectual effort. And despite skepticism from many, the solutions he was so confident in have worked flawlessly for over a century, and they continue to do so. But of course, first, we need to talk about the happiest thought of his life. Albert's story continues. Have you ever thought of something, an idea that brought you joy just by coming to your mind? Then, maybe, you high-five yourself in your head, give yourself a pat on the back. That's exactly how Albert felt when he spoke of the happiest thought of my life. The happiest thought of my life. What happens if a person jumps from the top of a tall building? Naturally, they don't feel their own weight. That was Albert's happiest thought. Now, you might think, what's so special about that? Even a 5-year-old could reach that conclusion. Setting aside the fact that a 5-year-old often has more revolutionary ideas than many adults, look how this one thought would shake the very foundations of physics as it had been understood since Newton's time and even before. Albert posed a thought experiment. Imagine you're in an elevator and suddenly the cables snap. What would happen? You wouldn't feel your weight. You in the elevator would start falling at the same speed within Earth's gravitational field. Now, let's change the scene to space. You're on a spaceship far from Earth's gravity. Here, you would float, weightless. But if the rocket suddenly accelerated, the floor would move up toward you, and you'd feel as if you were standing on solid ground, as though you were back on Earth, experiencing gravity. So, Albert wondered, could gravity and acceleration be the same thing? In a constantly accelerating rocket, there's no difference between standing there and waiting in a sturdy elevator. Gravity and acceleration, could they indeed be one and the same? Other scientists who heard about this idea merely thought, interesting, and moved on. But only Albert saw what would come of this, a revolutionary, entirely new theory of gravity. As Albert ascended to this nirvana of ideas, there was also someone he was neglecting, Mileva. They had once promised to stand together, to be each other's partner in every way, but Albert's priorities had shifted. He admitted openly during this time, "I'm not good with people. I'm not a family man. All I need is peace and the solitude of a single life." In 1911, the family moved to Prague, and their relationship continued to deteriorate. Their second son, Edward Einstein, had been born a year earlier, and now Mileva was entirely occupied with raising 2 children and managing the household alone. Albert, meanwhile, was climbing the career ladder and had started working as a professor at universities. Mileva's dream of being a strong woman in the male-dominated world of science was drifting further away. In letters from that period, she said, "Albert's success makes me very happy. He deserves it all. But I fear that his success and fame are eroding his humanity." Over time, she sank into a deep depression. She felt abandoned by her husband, who barely acknowledged her presence. She wrote, "I don't even feel like a person anymore. I've been deprived of affection and almost despise science for it." Albert's response was as indifferent as ever. "I can't spare time for loving conversations," he said, just as one can't play the violin while solving a difficult problem. By then, there was no turning back for him. His only priority was science. Gravity had consumed his thoughts entirely, and he continued refining his thought experiment. If gravity and acceleration were indeed the same, what could acceleration teach us about gravity? He returned to his space scenario. Imagine a light beam passing through a spaceship. As the rocket accelerates, the beam would appear to curve. So, he thought, if acceleration bends light, gravity must also bend it. He had found a clue, a lead to pursue further. It seemed that gravity didn't just pull an apple to the ground. There was much more. At this time, Albert was working in an office overlooking a mental hospital. Observing the patients, he thought, "I am a madman obsessed with physics," and he wasn't wrong. For the next 5 years, this thought would become an obsession. In 1911, the famous Solvay Conference was held in Brussels, attended only by the most prominent scientists, exclusively by invitation. Albert was the youngest scientist invited. Gabrielle, the daughter of the university's rector, later recalled, "There were physicists everywhere, big names. My mother nudged me and pointed out a young man, saying, 'See that man? He will be greater than all these physicists.' The man was Albert Einstein. This young man from the patent office was now discussing ideas with the likes of Marie Curie, Hendrik Lorentz, and Ernest Rutherford. Meanwhile, Mileva's worst fears were coming true. Albert was becoming more distant, and she longed to be recognized as his partner in every way. But Albert wanted a companion who would make no demands on him and simply manage his affairs, a role that his cousin Elsa would come to fill. Albert, it seemed, was truly inept in his personal relationships. After exchanging a few letters, he began an affair with Elsa but temporarily paused it to reunite with Mileva and the children when he returned to Zurich as a professor of theoretical physics. The same Albert who had struggled with teachers returned to his alma mater, not as a student, but as a professor. While his personal life may not have won admiration, his professional life flourished. He could now focus entirely on the problem of gravity. His former teacher, Hermann Minkowski, who had once called him a lazy dog, had read Albert's 1905 paper on special relativity and said, "I would have never expected this from him. This is extraordinary." Minkowski took relativity even further, expressing it with such complex mathematics that Albert initially didn't recognize his own theory. Minkowski was right. He stated, "Space and time are one, presenting a four-dimensional universe. Imagine a vast empty space where any event's position could be recorded with just 4 numbers. With just 3 coordinates, you can specify the location of any object, from the tip of your nose to the farthest galaxy. Length, width, and height are enough. Now, add time as the 4th dimension, and you can record any event from the Big Bang to this very moment, at any place and any time. Imagine you meet a good friend at a cafe. You're sitting at a specific point in the universe that can be described with 3 numbers, and it's exactly 10:10 a.m. Hermann Minkowski realized that this event, a meeting at a specific location, and time could be represented as a mathematical picture. Now, as you sit there, a second passes, then another. Your spatial coordinates remain the same, yet you are not truly static. You're moving through time. This concept was Minkowski's idea, and he beautifully interpreted Einstein's ideas. But there was one missing piece, which Albert would soon notice. This beautiful spacetime picture could not remain static. It had to bend. This was the point of transformation. What would happen if this magnificent fabric of spacetime bent? We had gone from a man jumping off a roof to this revelation. Spacetime could bend, and this bending was none other than what we know as gravity. Objects in space were connected as though by an invisible thread, exerting a pull on each other. Gravity, this bending of spacetime, was an incredible idea. And what caused this bending? Only matter and energy could do so. Imagine throwing a stone into a pond, creating waves. Those waves exist because of the presence of the stone. In spacetime, the bending we call gravity is similarly caused by the presence of a mass. When there is no mass, spacetime remains flat. But when a star is added, it bends the space around it, and anything near this bend follows its curvature. The answer to a question that had puzzled people for thousands of years was now clear. It was the bending caused by mass that held Earth, the Sun, galaxies, and clusters of galaxies together. Albert completed a preliminary version of this new theory of gravity, which we know as the general theory of relativity, in 1913, and even this incomplete version was enough to catch the attention of key figures. Who was the first to notice? The same Max Planck who once warned Albert against tackling gravity, saying he was taking a big gamble. Seeing that Albert had succeeded, Planck quickly traveled to Zurich to invite him to work in Berlin, the center of theoretical physics. This was an offer Albert couldn't refuse, and he accepted, moving to Berlin with Mileva and their 2 children. However, his relationship with Mileva was now beyond repair. Less than 3 months later, Mileva had had enough and returned to Zurich with their sons. Although separated from his children, Albert felt a sense of relief, accepting that he was neither a good husband nor a good father. Soon after, he resumed his relationship with his cousin Elsa, believing she would be a better match. Meanwhile, the outbreak of World War I shook Europe. 93 German scientists, including Max Planck, published a manifesto in support of Germany. Albert, however, was staunchly opposed to the war, launching a campaign against it, though he managed to gather only 3 signatures. He later said, "Europe is in complete madness, as though it has lost all reason. I feel ashamed to belong to this degraded species that calls its brutality patriotism." While the war raged on, Albert found solace in his theories. Only one obstacle remained. He had to express the bending of spacetime mathematically. For 3 years, he worked tirelessly, day and night, on this problem. Grossman, an old friend, would help by guiding Albert where to look, even though he didn't have the answer himself. Finally, after 3 years, the general theory of relativity, a theory so complex it even gave Albert a headache, was ready. In the fall of 1915, it was time to test it. Newtonian physics had always struggled to explain Mercury's orbit. This was Albert's theory's first real test, addressing a mystery that hadn't been resolved. Would his purely theoretical formula hold up? He calculated Mercury's closest point to the Sun and applied his formula, then waited for the result as if pressing a button on a computer and waiting for the output. The result, 0 deviation. Mercury's entire motion fit perfectly with his predictions. Spacetime was bending, and objects were following this curvature precisely. Even light followed this rule. For many, this theory was the dawn of a new understanding the fabric of the universe, the expansion of galaxies. Modern cosmology, it was all encapsulated in a simple formula. On the left side, spacetime; on the right side, matter and energy. And there was Albert Einstein, with his magnificent theory of general relativity, a theory that had begun with a single spark and led to a great illumination. You might think his story ends here, but no, Albert was not one to settle. His work was not done. He wanted the theory of everything. This child whose world had been changed by a compass, who had glimpsed the mind of God, wouldn't stop. He wanted it all, but it wouldn't be easy. There's still more to discuss and understand. It was 1919. One of the darkest periods in world history had just ended. Millions were gone, and those who remained were left with bloodstains and scars. But amidst the darkness, there were still those searching for light. A few years earlier, Albert had said, "Let me present to you the new law of the universe." He had completed general relativity and explained Mercury's orbital anomaly with zero deviation. And in 1919, this theory was about to be tested for the first time through observation. During a solar eclipse, Arthur Eddington put Albert's theory to the test, and as predicted, light bent exactly as Albert had proposed, proving the curvature of spacetime. Albert said, "Even if the results of Eddington's experiment hadn't aligned with my expectations, it wouldn't have mattered to me because I know my theory is correct. Otherwise, I'd feel sorry for God, thinking he made an error somewhere." Was this confidence? No, it was something else. This eclipse experiment did more than confirm his theory. It turned him into a globally famous scientist overnight. Here was a man who told people to throw out everything they knew about the universe because he was rewriting it all. At first, skeptics dismissed him, but after the experiment, they were saying, "Wow, he was right." All eyes were now on him, and newspapers were covering his every word. Albert didn't enjoy this attention. "Fame has made me stupid," he said. But perhaps he didn't take it too seriously. Charlie Chaplin once said to him, "You know, Albert, the thing I admire most about your art is its universality. You don't say a word, yet the whole world understands you." To which Chaplin replied, "That's true, but the grandeur of your work is even greater. Very few people understand you, yet the whole world admires you." It was true that only a few understood general relativity and its implications, but many tried to comprehend and explain it. In 1919, Max Fleischer, the creator of Betty Boop, used the technology of the time to create an animation explaining the theory. Everyone was talking about Albert. But one question remained. Was Albert the greatest of all time? It's a question we've been asking ourselves. Who was the best? There is no definitive answer. History isn't a competition. At every point, history has brought forth the best minds, and many of today's scientific achievements are echoes of the great minds who laid the foundation centuries ago. Science is a collective effort, and Albert was an important figure on that team. Humanity had just endured a dark period, and people like Albert became symbols of hope. Beyond the revolutionary nature of his work, humanity wanted to hear about something else, something brighter. For many, we are similar, aren't we? Gathered here, we do want to talk about something different. There is more to life than the clutter at home. Somewhere out there, discoveries await. We want to escape political conflicts, humanity's pointless power struggles, and talk about these discoveries or perhaps even make them ourselves. In every troubled time, there emerges a group like us. You are the torches that light up the darkness. Albert was one of the greatest, but he wouldn't have existed without the giants who came before him. So what happened next? Did the story end here? Was Albert's chapter closed? Not quite. Remember Mileva? After their divorce, Albert had promised her the prize money from the Nobel Prize. Albert wore himself out chasing this honor, so much so that his health deteriorated, and he nearly died. His cousin Elsa played a major role in his recovery, nursing him back to health, and they married in 1919. Was it a happy marriage? Sadly, not really. Albert continued to be Albert, keeping separate rooms, not allowing Elsa into his study. In relationships, he was a complete disappointment. He even admitted it, saying, "All marriages are doomed to fail. It's a futile endeavor. I can love humanity, but forming a bond with one individual is hard for me." He remained alone, but this solitude was soon disturbed. After World War I, anti-Semitism was on the rise in Germany. Some German scientists began dismissing his work as Jewish science, alienating him. Albert, who had previously not placed much importance on his Jewish identity, began to embrace it publicly. He once said, "I thank you for giving me the chance to express myself as both a European and a Jew." Though I may not fulfill all religious duties, I was born a Jew. As a child, I was deeply religious, reciting prayers out loud on my way to school. But when I read my first science book, I came to realize that behind everything lies a structure we can only partially comprehend. It was in this quest to understand that he questioned the nature of light, leading to special relativity and later, the bending of spacetime. He thought he had grasped part of the mechanism of the universe, but in 1927, Albert faced a turning point, a blow to his understanding of order. The 1927 Solvay Conference had arrived. Albert had, in a sense, captured a snapshot of the macro-universe and hung it on the wall. Everything fit that picture, creating a beautiful view. But as always, every era has its challengers. And in the 1920s, they emerged. New ideas about the nature of light and the fundamental laws of nature were developing, led by young geniuses like Niels Bohr and Werner Heisenberg. They were creating a new frame to place beside Albert's picture. At the Solvay Conference of 1927, the battle would begin. They spoke of uncertainty and randomness at the core of energy and matter in the realm of atoms and subatomic particles. Albert was striving to uncover order, but these new ideas contradicted his beliefs. He could not accept this. He simply couldn't. He said, "Quantum mechanics is successful, but there is no randomness. There must be something underlying this uncertainty, something to explain it. God does not play dice." Yet, as he struggled to prove this, Niels Bohr and his followers continually proved him wrong. Bohr even told him, "Albert, stop telling God what to do." With confidence, Albert sought a theory that would merge everything, a theory of everything. This would be a theory to explain both the macro and micro worlds, uniting all forces. However, it would not be easy. In the late 1920s, the Nazi Party was rising to power in Germany, and by 1932, Hitler was on his way to becoming its dictator. No one was truly safe, especially Albert, the world's most famous Jewish scientist at the time, who began receiving death threats. Just as he had in his youth, Albert realized he needed to flee Germany once again. Leaving wasn't difficult for him. As he once said, "Throughout my life, I've never felt like I belonged to any one country, not even to my friends, not even to my family." With time, I withdrew further into myself. Yes, such isolation isn't pleasant, but I've never regretted it. I've never needed others' understanding or sympathy. That freedom has given me the chance to escape their biases and opinions. And so, in 1933, Albert and Elsa set sail for America, where he took up a professorship at Princeton, seeking the solitude he preferred. In his quiet home on Mercer Street, he would take long walks, but never learned to drive, nor did he bother much with citizenship rules. Yet things would get even tougher for him. His companion Elsa passed away in 1936. His former wife Mileva would pass away in 1949, and he would never see her again. His son Edward, diagnosed with schizophrenia, spent his life in a Swiss asylum until he passed in 1966. His other son, Hans Albert, became a professor in California but rarely saw his father. While all of this happened, Albert was still in pursuit of that elusive theory. He never found it, and some may think he wasted the last 30 years of his life. But in reality, his search itself was a tremendous legacy. He questioned quantum mechanics and pointed out gaps, pushing science forward and showing others what to look for. Even today, many continue his path, seeking a unifying theory, a theory of everything that can tie together the laws, formulas, and forces of the universe. During the war years, Albert mostly stayed silent, although he did speak up to urge the acceleration of nuclear research, warning President Roosevelt of what could happen if Germany succeeded first. Contrary to popular belief, he had no direct role in the creation of the atomic bomb. After the war, people turned to him for guidance on almost everything. Once, officials from Israel even visited him on Mercer Street to offer him the presidency of Israel. Of course, that was a role he could never accept, and he politely declined. Science always remained his priority. The theory he was seeking, the elusive theory of everything, would be his final quest. By the spring of 1955, his health was declining. On April 15th, he called his secretary, asking her to bring his pen, glasses, and unfinished notes. He knew his time was short, yet he requested a calculator and started calculating. Whatever those notes contained, perhaps even the theory he had been searching for all of his life, we may never know. But for him, fighting for what he believed in, right up to the end, may have been the very thing that made him immortal. In the early hours of April 16, 1955, at the age of 76, Albert, the child whose eyes once sparkled with wonder at his father's compass, the man who cried out, "Look, I've figured out how the universe works," Albert Einstein passed away. And perhaps it was as meaningful as it could be. Knowledge is immortal. In writing his name into history, he left behind something even more valuable, a legacy of questioning, of seeking meaning. Albert Einstein, just a curious child like any other curious, with boundless imagination and a million questions, was the kind of child who had the potential to change the world. And he did. His name was Albert Einstein. And as always, until we meet again, thank you for being here. Don't forget to like, share, and subscribe for more content like this. And remember, you are valuable.